Hello. This is attempt number two at recording this. So on Tuesday this week, Sevsock asked me to do a crash course, and yeah, the audio screwed up. So we're gonna do the crash course for timber, and this is also part of my series on my YouTube channel. Check out the Sigma Lectures, the YouTube channel, where I'll be doing a couple weeks of the introduction of this course, first half of this course, I should say. I think this course has changed a lot since I originally did it, especially the second half. So I'll see what I can do in that second half, but expect the videos to slow down a little bit because I won't have materials ready, essentially. With that said, this course is really cool. I got really into timber after I guess simultaneously taking this course as well as doing my thesis, like undergrad thesis on timber related project to do with glue lam timber, which I'll explain in a little bit. And then I liked it so much that even before I started working as a grad, which I do now, as a structural engineer, before I started working, I got into a little woodworking phase. So yeah, you'll find that. Oh, and I'll get some examples as we go through this video on this. Like I have some offcuts basically from woodworking. So yeah, I guess without further ado, we'll get to my notes. So yeah, week one. So I guess how this course is broken up is into two parts. Week one, we're just talking about timber as a material, and there's a code. Let's write it down. AS, not that one. 1720.1, which is our timber code for Australia. And I guess like all timber structural engineering design revolves around this code. Yeah, and we'll get into the difference between sawn timber and EWPs, but this code documents both types. And also something else we'll need is AS1170.0, which is our load combinations, which if you've done steels and if you've done concrete, you'll know what those are, but we'll talk about it a little bit later. Yeah, and this course kind of tests you because essentially we're going to be analyzing a lot of 3D systems, structural systems, which is a little different to how you've kind of been taught concrete and steels. Because for those ones, you're kind of just given a beam or a column, and it's like a very isolated element. You're told what loads are going on it, and then it's like, okay, calculate how strong this concrete beam is. For this course, you'll find that it's a lot more applied. Like it's a fourth year discipline course for a reason, and you'll find that you kind of have to understand how structural systems work, and we might get into that a bit more, especially next week. But for now, we're just going to be talking about timber generally, its application in engineering. It's it's kind of biological properties, because unlike steel and unlike concrete, there's a lot of biological variation in the structural material, which is very cool. It leads to kind of in the code a lot of variability factors. So if you think of it like a spectrum in terms of the materials, you have steel as the most consistent material, and then you have concrete, and then you have timber as the most variable, because you'll find a lot of natural defects and just inconsistencies with how you can grade wood. So yeah, timber is very variable, and so it's very it requires a lot more of a fundamental understanding of how it works than the other materials in order to design for it. So yeah, let's get into the rest of the stuff that I've shown on screen later. Okay, so as I mentioned a little bit just now, you can have sawn timber and you can have engineered wood products. So sawn timber is basically like what you can buy off the shelf at Bunnings, or you can order from like manufacturers. Like in Sydney we have Blacktown timber suppliers, I think they're called, and those kind of timber yards, timber mills, timber suppliers. So in America, they call the woods by the cross section. So like 2x4s, 2x6, and this is like inch which I think is double dash. Yeah, you might have heard those terms before. That's just referring to the cross-section size. So like that dimension, and these are like products, right? And then if you order it from Bunnings or whatever, you can get it in like standard sizes. I think it's like 6 meters, I want to say. It's typical. Maybe like 9 meters as well. I'm not sure. But yeah, it's whatever like the mill size is generally. Okay, in terms of different grades of timber, so what a timber grade is basically they want to say you get like a pile of logs. You get logs and then you mill it. So you cut it and you process it into these kind of rectangular cross sections. So what makes one bit of sawn timber stronger than another, right? Well, there could be variations in the type, the tree. Some trees could be more mature than others. There could be variation in the species. There could be variation in defects, like natural defects. Say there was like a knot, right, in this bit of timber. That would actually be a structural defect. So we have to basically stress grade timber. Usually you can stress grade or you can like destructively grade a batch of timber where you completely break the plank of wood, but usually we stress grade it. So we there's like a little needle or something that pushes into the timber, and then it does like a very quick calculation on like stress on strain to work out the elastic modulus, so the material stiffness. And then actually that's how we separate these grades of timber. So like for example, we have MGP10, MGP12, MGP15. That would equate to 15,000 roughly in the code. This is a more specific number. MPa, timber stress, elastic modulus, right? And that process I just described was machine grading. So they get the little needle conveyor belt, boom, like test stress grade, and it's non-destructive, right? So you can still use the bit of wood afterwards, and then conveyor belt, stress grade, and keep going. So MGP is a very like what is pine firstly? So pine is a fast-growing type of tree, and the sustainable farms. Right, because one problem with timber is that trees can take a very long time to grow, right? Maybe up to 20, 30 years to mature, depending on certain types of trees. But pine is a type of softwood, right? And softwoods generally mature much quicker. In the sustainable radiata pine, which is the species, in these sustainable radiata pine farms, you can kind of be able to plant more trees than you could chop down, essentially. And so pine is a very widely used material for that reason, but it's not, its strength is okay, but usually it's on the weaker side compared to hardwoods, right? But anyway, we use it a lot, and we can kind of like mass produce it in this machine grading process. So this is a very specific type of product which uses radiata pine. Now, F-graded timbers are visually graded, so you literally have a timber expert, and you come in, and this guy comes in, and he inspects for any knots and uses his like engineering judgment to basically grade any species of wood, right? So he identifies what type of wood and can basically give it some kind of grade. And this follows a different system, essentially. But yeah. There's also another one called A grade, I think. This is similar to F grade, but I think it applies specifically to ash, which is like sometimes called mountain ash, sometimes called big ash in Australia, Victorian ash. Alpine ash, I think. Generally it's still the same thing, but it's like a visually graded hardwood species, which I'll talk about in a bit. But yeah, so sawn timber, that's kind of how it works. Engineered wood products, right? Sometimes called the shortened term EWPs, although I think that's just a term that people who write papers on timber say. like myself included when I was doing my research thesis, because I think in industry, it's more common to use the word EWP as elevated work platform. Like in trade, they'll think you're talking about this, which is like a type of, it's like a scissor lift, for example, is an elevated work platform. But in the context of this course, we're going to be calling engineered wood products EWPs, right? So there's various types. I've only listed a few, probably the most common ones, and I think these are the only ones that are in the code. Yeah. Um, yeah, it's actually not limited to this. I'll give some examples of ones which aren't as used like structurally in a bit, but I'll talk about these ones first. So glulam is basically used as beams. Generally, they're used for beams. So when you have a tree, right, and say that's your tree trunk, essentially you're limited by how big this cross section of tree is, right? And so it's very hard to create large cross sections unless you basically engineer your own cross section by gluing multiple pieces of wood together, right? So you can stack up, say, like 7, like 9 layers of planks, and you can get to pretty large member sizes. Yeah, so that's called glulam, and there's companies that specialize in it and create these like GL grade. It's called GL grade in the code products, right? Which are usually used in mass timber buildings. So mass timber. Okay, so there's like residential timber buildings. Sorry, I'm kind of info dumping, but there's residential timber buildings, and then there's mass timber buildings. So residential timber buildings are like your stick framing kind of homes. You see it a lot, I think. I mean, you see it everywhere, but like I think it really started in America, where you have, just like you might have seen like. I'm not doing a very good job explaining this, but like so you use like a series of like the sawn timber members, and usually these are treated pine. So you'll see the timber's like actually green or blue because it's been sprayed with insecticides or fungicides, so that if it rains, like you're not going to get like fungus that's going to affect the durability of your timber frame. Anyway, so that's very common in like residential timber construction. On the other end, we have like very large buildings. So those are like relatively small buildings. Those are your like 1-story houses, 2-story houses, and stuff like that. On the other end, you have mass timber structures, which are like skyscrapers, large office buildings, large bridges. Anyway, so you'll see mass timber. You'll see these engineered wood products generally used for mass timber buildings. Another one is like LVL. So LVL are laminated veneer sheets, right? So they're like laminated all together to create essentially large beams as well. So these are also used for beams. But the function, like the use case is a little bit different. You use more epoxy. So you can like as the essentially adhesive or glue, you can use epoxy, you can use polyurethane. I think those are the two most common ones. And this one, like, because you have more layers, you use more of the epoxy, and you can also, and actually ends up being stronger than glulam. It might be more expensive. I'm not actually too sure about that. But you can also curve your beams. So if you want to create this like parabola shape, I don't know, roof or something like that, you can do that with glulam over like large and large spans, but you have a lot tougher of a time kind of creating that curved shape unless you have these really thin layers which are very bendable. So LVL is quite good for that. CLT is similar to glulam, but you're using it usually to create like entire floors, right? Or like slabs, I guess you can call them. So you have like these large cross section, or these sawn timber cross sections, and you're stacking them next to each other in one layer, and then on top of it you have layers going the other way, so perpendicular 90 degrees, and then another one stacked on top. and you always have an odd number of layers. So you can have 3, 5, 7, maybe it goes up to 9, but I think that's getting pretty ridiculous. But yeah, so basically that ends up being more in one direction, like more running longitudinally in one direction than another. So there's something called a minor direction and major direction, and you'll find that's because here I've got a bit of timber. I think this is American oak. So let me just check if I can see myself. Okay, good. Is my mic working? Okay, good. I'm paranoid. So essentially, you can see these fibers running kind of like parallel. That's the longitudinal direction, and then you can see the cross section. This one's better. You can see the cross sections have all these like little straws. Actually, you can think of them like straws, and that's the end of the fibers. And basically, if we bend in this direction, right? So if we're bending parallel to the grain, yeah, you basically have stronger properties, right? So so the longitudinal direction runs this way, and there's 2 layers of that, and then in the minor direction, we have longitudinal layers running that way. So that's the minor direction. So if you think about calculations for this will come into play like in week 5 maybe. This is the cross section, and when we're considering CLT design, it's going to use a different code to the Australian code, which I forgot where I wrote. So it's different to that. We're going to be using Eurocode 5 for CLT design, right? So basically, to calculate like the effective centroid or neutral axis, I should say. So that's the bending axis, right? To calculate that, we ignore all the layers which aren't facing in our direction that we're considering. So if we're considering the major direction, which is what I've highlighted in yellow, yeah, the neutral axis will be like positioned in between that. So if we have 4 layers instead, right, the neutral axis becomes unsymmetrical. So it becomes like here and here. And so if we have this going on, and so actually you're going to end up with worse calculations than if you had an odd amount of layers. So that's what I'm trying to say there. The same principle applies to plywood, but just on a much smaller scale. So you've probably, if you've done like woodworking or anything, you've probably seen plywood, and it's like very thin, like, you know, whatever, like this would be like 13 layers of ply is like basically like, I don't know how thick it would be, like 3 centimeters or something like that. And so yeah, you have, oh, maybe not 3 centimeters, maybe like, yeah, maybe about 2.5 centimeters, whatever. So yeah, that's what happens when you have an odd amount of layers. Like it has better, more dimensionally stable properties. Okay, cool. Because I normally like would record these weekly in front of people. I would like stop and ask if people have questions, but because it's just myself and I'm recording this offline, I'm just gonna be rambling. So yeah. Okay, so standard sizing, as I mentioned, we kind of have these trade names, American trade names, right? And you have like 2x4s and 2x6s and etc. But in reality, there's the real dimensions. So this is in inches, right? A 2x4 would actually be 1.5 inches by 3.5 inches. And in my opinion, like this comes down to the whole processing of the timber. So if you have like a tree log like that and you're cutting it, right? And so you're just cutting it like that, right? The blade has a certain thickness which erases material. And so if we're trying to, I don't know if this looks exactly like this, maybe like that. If we're trying to make a 2x4, I'm just gonna do this in inches because, yeah, whatever. And we're doing something like this, right? Because our blade cuts and does that, we've eliminated some material already, right? And then this stack of rough sawn wood gets placed, and it came from a live tree, so it needs some time to dry and It's in a process called seasoning. And in that process, it's going to shrink a little bit and warp. And so we're going to get some undesirable properties. Now, at this stage, if you want to refine your wood to be perfectly square, as in like these cross sections perfectly square, we're going to have to erase material again. And in that process, we're losing more and more of our cross-sectional dimension. Cool. So that's how that works. So those were American kind of units. In Australia, we have various depths, right? We have 90, we have 120. These are the standard depths. 140, go back to red, 190, and 240, right? The list goes on, but I've just included the common ones. And between these, you can see that we have two standard widths as well. You have the thinner one, which is 35, and you have the thicker one, which is 45. And those will have different kind of use cases as well. Yeah, so that's kind of how that works. And think of the sizing like you can make your own section sizes, but these are the ones that are milled and mass produced. And yeah, it's like it's good to have standard sizes. It's similar to Lego. So, you don't want all your Lego to be like slightly different sizes because then they can't fit together, right? So, yeah. Anyway, think of it like that. They come in standard sizes essentially. Okay, so, milling process. We have a few different types of like the way that wood is sawn, and this will tie into something we're going to talk about in a second called shrinkage. But you'd think that this is like pretty trivial, right? Like how you cut the wood doesn't really matter, but in reality it does, and that's because wood is an anisotropic material, right? Which means it has different behavior in different directions. Now, isotropic materials basically is something like steel, right? Where it has similar properties in any given direction, essentially, right? But anisotropic materials don't, right? And there's a very specific type. It's not specific. It's more of a simplification. Because timber is a very complicated material, and we want to kind of be able to have an approximation which can cover most cases, and so we simplify it to be orthogonal, orthotropic. So orthogonal means like at 90-degree angles, right? So if you have your X, Y, Z directions, those are orthogonal to each other, right? Similar idea for timber. So I'm gonna draw this in 3D. One direction is longitudinal, right? Longitudinal. Another direction is radial. So what I mean by radial, right? So you see the growth rings, right? So in the direction of the radius, like an increasing or decreasing radius, that's the radial direction, right? And then tangential. Tangential is just like tangent to that, right? And so essentially, if the cheapest way to mill a piece of wood is flat sawing it. So your saw doesn't really need to change directions or anything. It just processes the wood in a very like straightforward way. But then you end up with these pieces of wood, right? Which if you go to Bunnings, you'll see this quite commonly. If you're buying like MGP or whatever. Now, quarter sawn wood is processed a little bit differently. So you cut it into quarters firstly, and then you get those quarters, and then you process it as such, and then you'll end up with these kind of pieces, right? Because like, let's just say for example that it's like that piece, right? So you get these ideal kind of pieces in the middle, but a lot of your pieces will be off to the side, and so you kind of get this diagonal kind of cross section. Actually, yeah, this bit of woodworking offcut that I have is like Victorian ash, and so you can. I hope you can see that. You can quite. Oh fuck, the light. It's pretty bright. Yeah, hopefully you can see that. Yeah, there we go. Look at that. See these beautiful lines. That's like one bit of wood. You can see these beautiful lines, and that's the growth rings, right? Which represents 1 year of how old a tree is, right? Okay, so where was I going with that? So rift thorn, you can see that these growth rings are perfectly. Oops. You see that these growth rings are perfectly like kind of in line with each other, and that's if you keep turning your blade or your material that you're trying to cut, right? So why does this actually matter other than the fact that maybe it looks nice? Well, something happens in wood called shrinkage, right? As you can imagine, your piece of material will want to shrink due to various things like moisture condition in the air, like temperature. And yeah, this is like a process that happens over time, right? Now, yeah, like I was saying before, we have a longitudinal direction, radial direction, tangential, and the graph on the right, you can see how much of a difference. I think you can especially see it on this side on the left. How much of a difference these three directions get relative to each other in terms of shrinkage, right? So the least shrinkage happens in the longitudinal direction, right? So if we have a bit of wood like you see here, like the direction where I'm pushing it or I'm pulling it, that's the longitudinal direction. It's not going to shrink basically that way. It's like a very negligible amount of shrink. But in the cross sectional kind of directions, right, radial and tangential, you're going to see a lot more shrinkage, and especially in the tangential direction, you see the most shrinkage. Yeah, so this leads to warping defects induced by shrinkage, right? So cupping will especially happen the most when you have this like flat sawn piece of wood, right? So this will want to basically cup like that, become a sad face like that, and obviously then your wood won't sit flat, and that's not very optimal. That's one type of defect. We also have bowing. So this happens when you have a like fairly long piece of wood that's say it's like that, right? So one side's flat. In the weak direction, if I'm looking like straight onto it, so if my eye is like here, you'll see it bow out like that, right? In the middle, maybe like here, right? You can see this start to bow out like that. So yeah, again, it won't be flat if we're resting it on its minor axis like that. It won't be flat, and you'll see this little bit stick up, which, you know, is not ideal. Crooking is less likely to happen because it's in its major direction. It'll be bending about a stronger axis, so crooking doesn't happen so much. Kinking also doesn't happen so much. It's probably more so due to like a knot or something being here. I don't know if it's that side or that side, where it's grown differently, or like kind of like physical damage or something could cause kinking. Twisting, maybe the grain is like orientated diagonally, and so its tangential and radial directions are slightly opposite, and so it might twist a little bit. And one way you can test if something is twisted or not, I don't know if there's a good example, right? So say you get like a piece of wood like this, you put it on a table, and you put your fingers on opposite corners, and if it's rocking back and forth, it's twisted. Right. So yeah. Okay. Wood species. So we have softwoods and we have hardwoods. As I mentioned a little bit earlier. Now this is a little bit of a misnomer because this is just what we call coniferous trees and deciduous trees, but it's not actually like it's an indication of how strong the piece of wood is. But in reality, we have exceptions. Like we have hardwoods like balsa. So if you've ever, I don't know, done like a little science project where you had to use balsa, or like architectural project, that's like the toy wood that you're basically getting, that you're using, and it's like so light. It's as light as like foam pretty much. And so that's a hardwood. Like, come on. It's just because how it's grown is deciduous, right? But yeah, generally speaking, this is true. Softwoods grow much quicker, right? So that's one thing. These take about 5 years or so to mature, whereas these take like 20 years or so. Um, and so yeah, there's ups and downs to using both. The probably the number one downside to using hardwoods is sustainability and just really being able to replace the wood. But yeah, anyway, so some examples that are everywhere for softwoods, but in Australia, we'll see radiata pine. I think it's originally a European tree, but yeah, it's grown in Australia. It grows very quickly. It's kind of spread all over the world now. And Douglas fir is another one. Douglas fir will have very prominent kind of growth rings, and they're very like orange. So if you see like a bit of Douglas fir, you'll see that these growth rings have quite dark markings for their growth rings. And yeah, again, the whole thing's like orange. Another thing about softwoods is they dent very easily. So like these ones are hardwoods and stuff, right? And so if I put my finger in it and like if I put my nail in it and try to scratch it and stuff, it's not really gonna dent it much. But doing that on softwood is a different story. Like it's gonna make a mark and stuff. Yeah, and then for hardwoods, these are more specific to regions of the world because they're harder to like kind of plant and farm in different conditions. So these are like Australian hardwoods that we're talking about. We have gum trees. So common ones that you might see in like woodworkings like blue gum, spotted gum, that kind of things. We have Victorian ash or mountain ash or alpine ash, which is a trade name. These are all kind of trade names. Same with Tasmanian oak. Like yes, it's grown in Tasmania, and Vic ash is grown in Victoria, but they're not actually types of ash and oak like you would see in America. They're actually eucalypts if you look at their like family biology. Yeah, and obviously gum trees are eucalypts. Ironbark's another one you see in Australia. So ironbark is like the bark is like really hard, so they'll blunt like tools if people try to like cut them down or like try to put nails and stuff in them. Yeah, you're gonna blunt your tools because the bark is so hard. And another one is ironwood. Ironwood's incredibly heavy. So is ironbark. Ironbark's relatively heavy as well. Yeah, blackwood is a type of acacia. That's pretty common. You see in Australia as well. It's basically Australian. It looks like walnut basically. It's very walnut like, which I think people like to use, but it's a lot softer. And yeah, as I said, balsa wood. So a little fun fact about balsa wood. I went to go buy timber once for woodworking, and then like they said they ran out of structural like balsa wood because the last time people bought it was like years and years ago when they were trying to film like I think it was the Matrix movies or something in Australia, like sequels to the Matrix movies or something. And then they bought a bunch of balsa wood to use as like the walls that they're just gonna karate kick through. And so because like the wood's so soft, it's like relatively safe to do that. Yeah. Anyway, densities. So water is 1,000 kilograms per meter cubed, right? And so relative to that, we have for our softwoods, right? We have a design density lower than that. Like all of these are lower than that, which means that they can float in water essentially, right? So if I chucked a bit of pine into water, right? If I just chucked a plank of pine in water, it's lighter, so actually like end up floating to the top, right? Yeah, something I want to touch on as well, which I haven't, is the fact that things can be seasoned or unseasoned, right? So seasoned means it's dried and it's dried properly. Unseasoned means it's not fully dried, basically, right? And so when you cut down a tree, it's going to be unseasoned because it used to be like breathing. It used to be alive. You know, you used to have water running through its veins. Like humans, like 70% water or something, right? So like, I don't know what percentage a tree starts off as, but it takes a while to dry, essentially, right? And there's a rule of thumb that I learned like during woodworking. Let's just draw it as like a cube, or not a cube, but like a square prism. If that's a bit of wood, right, and it's unseasoned, it will dry at a rate of 1 inch per year, right? And so if you go to like Facebook marketplace and you see all this timber that's much cheaper than what you can buy on the market, and you go there and you buy it and you realize that it's not dry, So a lot of the costs involved in timber is from drying costs, because you have to leave it in some dude's shed for like a couple of years before it's actually usable, structurally, as well as like for woodworking purposes. And I say like for woodworking or like for furniture making, because you don't want your wood to move after it's, you know, been done to make like a beautiful like woodworking box or like a table or something, because yeah, it's gonna shrink and warp due to this process of drying, essentially, right? Anyway, so yeah, that's something to consider. Atmospheric temperature is, I don't know, I think it's around 10 to 15%, depending on where you are, unless you're in like very northern Australia, like upper parts of Queensland, upper parts of Northern Territory and stuff like that. So yeah, that, like when you're lower than 15%, you're dry, basically. If you're greater than greater than 15% is like not fully dry. There's another threshold number, 25%. Yeah, and then if you're between 15 and 25%, you're like partially dry. Anyway, what we're talking about? We're talking about densities. So yeah, hardwoods are generally more dense than softwoods, as you can imagine, and some of these numbers are above 1,000 and some are below. So, and it also depends on whether it was unseasoned or seasoned. So, yeah, basically, if it's greater than 1,000, it's going to sink in water, right? Okay. Okay, so question 1: timber is stronger. Timber is stronger in one direction and weaker in another. In which direction, perpendicular or parallel to the grain, are the engineering properties of timber stronger? B, what makes this phenomenon true? Explain. So when we're talking about parallel or perpendicular to the grain, right? So that's the grain, right? Running left to right from what you can see here. Parallel to the grain is the longitudinal direction, right? Perpendicular can refer to this way, right? Or like this way. In and out of the page here, or up and down, right? So basically parallel to the grain, I'll show you. Oh no, I'll show you in a drawing. I'll do a rectangular prism. So parallel to the grain, let's just say tension, right? Tension parallel to the grain is going to be stronger than tension perpendicular to grain, right? Because we're splitting the fibers apart, essentially, if we're doing perpendicular. So you have to understand from a material science perspective what a composite material is, right? Because that's what timber is. It's a composite material. We have a fiber material and we have a matrix material when we have a composite material, right? So your fiber material in this case is called... Your fiber material is called cellulose, right? So cellulose are like little straws. You can think of things like bundles of straws, and that's going to help with understanding like the bending and all these other properties, mechanical properties of timber. But yeah, so they're like little straws, and then if you bend it, right, the fibers is what's giving it strength, essentially, right? But if we pull it, the light just turned off. If we pull it perpendicular to the grain, we're actually relying on the strength of the matrix material, which is called lignin, which is like the glue that binds the whole thing together, right? So if we're pulling it apart, we're not relying on the strengths of the fibers anymore. We're relying on the strengths of the matrix in between, right? Okay. Question 2. The following questions are related to seasoning and timber. What does seasoned timber refer to? B. Which type of timber has superior engineering properties, seasoned or unseasoned? We've kind of talked about this. How is we haven't talked about why. How is the seasoning of timber taken into account? So, yeah, I've talked about this part. We have like different moisture contents, and then based on that is how dry timber is, and then we call that seasoned when it's dry. B. B was which type of timber has stronger properties. So seasoned timber has less properties. So essentially, if I go back to this, right, if we're in bending, I apply a perpendicular force, right, which causes compression at the top. Let's say there's like a beam basically, and tension at the bottom, right? These individual fibers are trying to slide against each other, right? And so water acts as a lubricant and enables this sliding process more easily, which is a bad thing, right? Because we want them to like act in unison. And so yeah, less moisture means better mechanical properties. So the last part is like, how is this taken into account in the code? I've listed some examples here, but to be honest, you don't need to know exactly all these terms yet, because these terms will cover throughout the term, right? So yeah. Okay, question 3. You're designing a flooring system and its supports. So this question is like, how do I? This question is basically getting you used to the terminology involved in like timber floor design, I guess, right? And there's quite a few terms, and some we haven't talked about yet. But like, you basically have to think in 3D to understand how these structural systems work, which is a little bit unusual if you've only done like concrete and steels, right? So let's go through this slowly, right? So you're designing a flooring system and its supports. The expected ultimate and service loads are 5 and 3 kPa. So I know at least one of the viewers of this video hasn't done steels and concrete, which means they don't really know what ultimate and serviceability loads are. So I'll go over that briefly, right? So in the code AS 1170.0, we define load factors, right? So I'm going to go through an analogy. You might have heard me talk about this before if you've watched some older videos. But let's just say we're looking at scaffolding. We had to design some scaffolding, and we had to design it for 3 tradies. Each of these tradies is 100 kilograms heavy, right? So when you're designing this scaffolding, you know it's going to hold 3 tradies. Are you going to design it to essentially be able to only hold 300 kilos? Probably not. You're going to introduce some kind of factor of safety, right? And so we have different words for this, right? What you're going to do is you're going to under-exaggerate how strong your scaffolding is, right? So that's called a capacity reduction factor, which is a form of factor of safety that we use in Australia, structural design. And usually that's denoted by phi, right? Now, in the timber code, it works a little bit differently because we have something called K factors, right? And we'll cover this next week. But K factors are generally reduction factors. There are a couple that are modification factors, which means it can reduce the strength or it can increase the strength, but generally they're reduction factors. So unlike the other codes, which just have your phi factor, we also have to account for K factors in timber. Okay. Now, so sorry, these were part of the timber code, which is 1720.1, right? Now, like, just from a loading perspective, right? Because this isn't exclusive to timber, this isn't exclusive to steel or concrete, this is just loads in general. You have to exaggerate the loads. You have to pretend that these tradies, instead of being like 100 kilos, you have to pretend they're like, I don't know, 120 kilos or something, worst case scenario, right? And so in this code, our load combinations code, we have exaggeration factors basically, right? And there's a couple for strength design. We have 1.2 G plus 1.5 Q. We have 1.35 G. We have 1.2 G plus W, which is downwards wind. We have 0.9 G minus W, right? So those bottom 2 are wind cases, which we'll probably talk about a bit later in this term, but these ones you've probably seen more commonly in concrete and steels. And so, yeah, okay, so firstly, what's G and what's Q? So G are dead loads and Q are live loads. Both are gravitational loads, but it depends on, we're talking about how long these loads are applied for. So dead loads can include the self-weight of the material. So say you're designing like a timber beam, right? You have to account for how heavy the beam itself is, right? That's self-weight. The other one is superimposed dead loads. Superimposed dead loads is after construction's done, like what what's going to be put on top of the structure, right? And you're expecting it to be there for years and years and years. So that's dead loads. Live loads are kind of like everyday loads. It's going to be on and off loads, or loads which you'd maybe expect for like a year, or it really depends. This is like a pretty general category. You can include everything from like pedestrian traffic to animals to snow. If you have an area which snows temporarily, that's a live load. Vehicles, yeah, those are all live loads basically, right? So you basically, because you don't know as much about live loads, like they're more variable, you have to exaggerate them more. So that's why there's a 50% increasing factor for live loads, whereas dead loads are more consistent. And so we only have a 20% increasing factor. Okay, cool. Does that make sense? Yes. Yes, it does. Okay. Service loads. Fuck, I haven't talked about this whole thing yet. So that was just strength. We have service loads as well. So service loads are everyday loads, right? And let me write down what they say in the standards, right? You have G plus phi S Q. You have G plus phi L Q, right? So this is the short-term factor and this is the long-term factor. Long-term factor is 0.4, short-term factor is 0.7. So unlike before, instead of exaggerating the loads, we actually under-exaggerate the loads a little bit. And this is because these service loads are everyday loads. It's like what you'd expect on a typical day. For like the service of this structural member, right? And so in the short term, you'd actually see you'd see a higher factor. And so an example of this is like, imagine the loading on like a classroom floor in a uni, right? In the short term, say like the terms just started, you know, it's like a week or whatever, and there's just like lots of people walking around, right? And so the majority of the floor is going to be loaded with people, right? Let's just say. So in the short term, it's 0.7. In the long term, you have to consider the fact that this building's not going to be occupied all the time. Like in, say, the holidays, right, during this uni term, you're not going to be loading it. And so your sample size is increased over time. And so generally, law of big numbers has now just reduced the live loading because it's not going to be there all the time, right? So that's kind of how we design our buildings and bridges and structures, right? Service loads, those are the kind of the numbers that govern. Okay, cool. So, sorry, where was I? Let's talk about timber now. So the floor is bounded by two 300 mil deep and 75 thick unseasoned F11 hardwood bearers which span 5 meters. That's one bit of information. Next bit of information. They bear on 200 mil thick 5-layer CLT walls. The floor joists that sit on these bearers are 240 deep and 35 thick MGP12 pine which spans 6 meters, right? And the joists have a center of, the joists, that's still part of the same thing. The joists have a center spacing of 1,250. The floor joists that support 30 mil thick 13 ply flooring nailed to the joists at 500 centers, which run the length of the floor. Okay, that doesn't matter. There are no overhangs of the joists and bearers beyond the floor system. Okay, so the first thing you gotta ask yourself when doing this question is, what the hell are floor joists and bearers and stuff like that, right? So I think probably the most intuitive one that you can think of at the start is the plywood flooring, right? Because you kind of know what plywood is, you kind of know what a floor is, right? So it might look like that, right? And it's saying that this is 30 mil thick, 13 ply, so there's 13 layers of ply in this floor, right? So 30 mil thick is not very thick, right? And so if you imagine yourself standing on that and it's spanning in one direction, it spans 6 meters, and the other direction it spans 5 meters. Like, you're gonna fucking punch a hole through this plywood, right? If that was like all it was supported by, it would deflect so much and probably break, right? And so we have to basically account for a person. How do I do this? Okay, imagine a person's here versus here versus here versus here versus here. There could be various point loads, right? So we're gonna have to spread out the loads somehow, and give this kind of bit of flooring stiffness along any given portion. And so the way that we do that is we introduce floor joists, right? So floor joists have regular spacings like this. The floor joists orange. Sorry, let's do that in orange for clarity. So these are the floor joists, yeah. The floor joists have some kind of center, right? So here it says the floor joists have a center and center spacings of 1250. They also have certain dimensions, right? So in terms of the dimensions, they are 35 thick and 240 deep, right? That's your cross section. Okay. Do I have to explain anything else about that? I'll probably have to talk about the nailing, right? So the floor has to be nailed, right, at regular centers to these floor joists so that it doesn't slip around. So these nails are at 500 centers, right? So hopefully that makes sense. Next is I'm doing it like top down, so as a structural system. Gravity like finds its way downwards, right? So essentially the loads will go, will spread out, right? So you can pretend that there's like a uniformly distributed load over this entire thing, right? And it's gonna want to go from the floor into these floor joists like that, right? These floor joists are gonna be simply supported, and the weight, right, of whatever it carries is gonna have to go land on these bearers, right? So floor joists and bearers, they are physically the same. There might be different members, but they're essentially just sawn bits of wood, right? But they serve different functions, right? Generally, bearers are a bit bigger because they're picking up the floor joists, right? So they are 300 deep in this case and 75 thick. And the question says two of them because you have one on either side to support the floor joists, right? The joists, right, they're spanning, what does it say, 6 meters, but the bearers are spanning 5 meters like this, right? So yeah, that's our system, but we're not done yet because those bearers, they bear on these CLT walls, right? Which are going to act as our essentially supports. Like we're just going to pretend that no amount of vertical load is going to be able to move these CLT walls. That's what a support is at the end of the day, right? Like just something that you're assuming isn't going to move. Okay, so that's our structural system essentially. These CLT walls, there's 5 layers, so I've drawn it a bit wrong. The 5 layers, yeah, and the whole thing is 200 thick, like that, right? So that's basically what is happening. So let me continue the load thing. So following these arrows, right, load will go onto these floor joists, right? So we have the edge joists, which are picking up this much load, and we have the internal joists, so they're picking up double the amount of load, right? That's the concept of trib width or trib area. Tributary, you can look that up, but it's basically just saying like, okay, what portion of the load is the structural member capturing, right? And then at that point, the loads will go like here, and they go here into the supports. So there'll be a certain load there, which would be a point load. There'll be another load here, which would be a bigger point load because these are the internal ones, and then a lighter load at the edge as well. So you have these bearers that are going to be taking, in what I've just drawn, which I don't think that's accurate. I think there'll be more floor joists rather than, yeah, do you know what I mean? Because like this divided by this, there's not going to be 3 spaces, right? I've just drawn it a bit simplified, slightly wrong. But yeah, so there'll be a certain amount of point loads along there. And yeah, then those will be supported like that. pin on the walls. So yeah, basically bending moment diagram wise, boom, boom, boom. And the bending moment diagram for this one is going to be a UDL, uniform loads. Those arrows are representing the amount of reaction on these supports, right? That's the reaction. I'll highlight that in blue. I'm kind of doing a very rushed job at explaining this, but I think the more practice you do, the better you will understand like kind of load paths. This is the load paths, right? And how the loads will go from member to member. So that's thinking in 3D, right? So yeah, to reiterate, that's all this stuff. I don't think I talked about, so F11 is just a type of F grade 11, right? Unseasoned means it's not fully seasoned. MGP 12, yeah, so this is a product of MGP. 12 is a grade. Here's what the system would actually look like. So yeah, basically what I was trying to say before is I drew it like this on the bearer. Yeah, like that. That was the wrong amount of spacing. It should have been, instead of 3 spaces, it should have been 4 spaces. Yeah. Yeah. So it follows load path, right? So we talked about it top down: plywood, joist, bearers, CLT walls. Sometimes these CLT walls would be like columns or something instead. Yeah. We talked about this. Yeah. Okay, so what other key aspects do you consider before you can consider this design complete? So there's basically something called creeping, which is kind of prominent in concrete design, but also especially timber design. And it's like basically not likelihood. It's the tendency for timber to move over time, right? And this has a couple flow-on effects. Firstly, we have K1 factor, which we'll talk about next week, which affects its strength design. And basically, like, if I had a timber board, right, between my bed and this table, and I put a big rock on it, say it doesn't fail, right? But if I left it there for 50 years, there's a chance it fails, because timber will lose something like 45% of its strength over time, over a very long period of time, 50 years. And this is due to creeping, right? That's approximate. That 45% is approximate. But we'll talk about that next lesson. Yeah, so that's one. And then 2 is deflection, so it'll deflect more over time. So as well as like its actual strength and capacity, it's also gonna deflect more over time, which you don't really see creeping happening in like steel, for example. Yeah, fire loading. I mean, I talked about this quite a bit the other day, but I just found out this isn't really in the course anymore, so I won't talk about this too much. But yeah, if you can imagine, like for timber structures, a big component is considering like the fire design. And so timber will like char and it forms this protective layer, and you have to like design for a certain fire rating period, and that just means like how long it can, like its cross section will last before it fails in the fire loading case. Yeah, anyway, that's a summary, but we won't really talk about it too much in this course. Oh, I've done a good job describing it here. It's the material strength after X amount of time affected by fire. So for example, 120 minutes, we have to fire rate and make sure that it doesn't fail for, right? Okay. Let's see. Connection design. We're going to talk about this in week 4. But essentially we have like, you have 2 bits of wood, right? You want to connect them together somehow, right? You have to consider the grain direction, end grain, side grain. You have to consider the type of fastener you're using. So fastener is just basically like, fastener is like kind of an umbrella word for nails, screws, bolts, coach screws, right? Small connections, yeah, you can use a nail gun and nail 2 things together. It gives it good kind of like shear strength. So if this is the nail and this is the 2 members, it prevents like this kind of shear, right? But in pull-out failure, the nail is going to pull out, right? Screws have better grip in axial. So they have the little threads which can bite and prevent this kind of like axial pull-out failure. Similar idea for bolts and coach screws. So bolts, they both have threads, sorry. So they're both more like screws, but just bigger. Bolts, you basically have to pre-drill a hole and then you insert the bolt. Whereas coach screws, it has like these teeth that can bite in as you're applying torque. And so you don't necessarily need to pre-drill for screws, for coach screws. Coach screws are basically just giant fucking screws, basically. Okay, lastly, we'll talk about kind of like a statistical thing, right? So when calculating deflections of 10 joists in a floor system, which elastic modulus should you use, the E mean or the E 5%? So E here is talking about its material stiffness, right? And then transfer beam, which elastic modulus should you use? So 10 floor joists in a floor system versus that. Okay, so first you need to know what they're talking about here. So statistically, right? So you have a pile of 100 sawn bits of timber, and you measure all of their stiffnesses and you line them up, right? So weakest to strongest, or like least stiff to most stiff, right? The 5th percentile stiffness is basically the 5th worst one. So you have your extreme outliers. You have the ones with like fucking a million like knots in it for whatever reason. And then, you know, your 2nd worst, your 3rd worst, your 4th worst, and then boom, the 5th worst one is the 5th percentile, which is what we designed for. Because basically in the case of a transfer beam, from the mill, you don't know which piece of wood you've picked up, right? You could have picked up one in the middle. You could have picked up one which is slightly worse. You could have picked up one that's slightly better. But obviously we want to be conservative and we don't want to pick the 5th worst one, right? And design for that kind of worst case scenario. It's a little bit different so I answered part B, but part A, right? It's a little bit different when considering 10 floor joists, right? So you go to the timber mill, you pick up 10 out of these 100 available sawn bits of timber. Statistically, you're not going to get the 10 worst ones, right? You're going to get like one in the middle, you're going to get one that's slightly better, one that's slightly worse, and so it all evens out, right? When you have like 10 of them, right? Because it'll be more closely represented as a middle, and so you can represent it as such, right? Okay, that's it. I'll stop talking now. Hopefully this recording didn't fuck up.